All right, welcome to today's lecture. We will be talking about stability of nuclides, or stability of the nucleus and its isotopes. This is Nuclear Chemistry Day 3, if you're following along with my class. The objectives for today are review the definition of isotopes, identify the patterns of stability or instability of isotopes, predict the likely modes of radioactive decay, and identify the relationship between half-life and nuclear stability. All right, so here we go. First off, isotopes. What is the definition of an isotope? An isotope is, as you remember, it's simply the same element but a different number of neutrons. So we may have uranium with a mass number of 234, or uranium with a mass number of 235, and then possibly uranium with a mass of 238. It still has different protons. It still has 92 protons all together, but it will have a different number of neutrons. Same with carbon-12, which will have 6 protons and 6 neutrons. We also have carbon-14, which has the 6 protons that make it carbon still, but now it will have 8 neutrons, therefore the mass number of 14. So the next definition we need to go over is nuclear binding energy. This is the energy required to separate an atom or an atomic nucleus completely into its constituent protons and neutrons. So each individual proton and neutron that make up the nucleus. It's also the energy that would be liberated, or the energy that would be released by combining the individual protons and neutrons into that single nucleus. Okay. And next, let's look at this graph. So here we have the nuclides by binding energy. We have the number of protons over here, the number of neutrons. Some scales that you see are some of the graphs that you'll see. Protons and neutrons may be flipped, but you need to be able to identify which protons are where, and so on and so forth. Okay? And let's see if I can get this back. There we go. All right, and so here, number of protons. Notice how this Z equals 82. Z is the number of protons. And so we start to see this change. We have the lowest amount of binding energy here at less than 6,993 is the dark red or the maroon. And then the highest. So all of your highest binding energies are here. Okay. Now, this is from the range of, starts from about atomic number 15, and right in the area of atomic number 51 is where we reach our maximum binding energy. And 51 would be iron, if you remember. And so some amazing things happen once we no longer have the full strength of that binding energy. And we'll talk about that at a different day. Notice this line right here, the Z equals N line. Okay, that's at exactly 45-degree angle. And that's always important to note when we're looking at any graph. At our 45-degree angle, if we take a mental note, some crazy things can happen. Okay, but this is where if we have 50 protons, we must also have 50 neutrons right here. We're on the graph, okay? Therefore, we know which element we would be on, and we know that it would have the same number of neutrons. Take a look at how this bends. As we increase in the number of protons, what happens to the number of neutrons? Okay, do we increase or do we decrease the number of neutrons as the ratio of neutrons in comparison to protons? Okay, take a moment, hit pause, think about it. Okay, and so now you're back. You can see that we must have more neutrons as we go here. We're still at atomic number 50, or let's do atomic number 60, but all of a sudden we now have 82 protons if we're in the middle. Okay, and so you can see as we get bigger, as the nucleus gets bigger, it needs more neutrons in order to have stability. Okay, we can see that here as we are at atomic number 40. To be in the center of the blue, we must have, if I can get my mouse to show up again, we must also have 50 protons. So 40 protons, and yet we need 50 neutrons. As we come all the way out here to get to the center of the band, we have 82 protons in the center right here, yet we have nearly 120 neutrons to bind together those 82 protons. So that is a trend that we see. Okay, and therefore that is one of the patterns of stability within isotopes. The larger we get, the more neutrons we need. Okay, and once again, here's our binding energy expanded, just a little bit easier to see it. Okay, and so now nuclear half-life. What is nuclear half-life? That is the time required for 1/2 of your substance, or 1/2 of your atoms of a given amount of substance to disintegrate, or to split apart and be from alpha particles or beta or whatever, half of the time that it takes for it to split and become something different. And so we can see that with this slide here. Once again, we still have our number of protons and our number of neutrons in their respective spots. Here in the black, I want you to take note of that. In the black, those are the stable atoms, or the stable isotopes. Okay. Once again, here's our 45-degree angle where Z equals N. And we see the band rolling so that we need more neutrons in comparison to protons. But notice how the stable isotopes are mostly in the center of this band. Okay, as we get farther away, if we look at the half-lives, here it's the half-life, or in the maroon, the stability of these atoms, if it's not completely stable, it would be greater than 1 × 10 to the 15 years. Okay, here if we go to, this is per seconds. If we go to the blue, this would be to the -12. Okay, 1 × 10 to the -12. That is a short half-life. So the farther away we get from the stability line, the shorter the half-life. What I want you to take away from this is that different isotopes for the same element can have a different half-life. Okay, it might be fairly stable and therefore its half-life is significant, or it may be, as we see in these light blue to dark blue bands, it may be pretty short, and it may be a matter of minutes as opposed to millions of years. Okay, so take note of that. Once again, here we've got, actually, if we look at this right here, atomic number 82, this is lead. Look at all the different isotopes. As we run this line laterally or horizontally, we have all those different isotopes for lead. All the way out here on this horizontal line, or this lateral line, we see all of these half-lives that are very short, all these isotopes that are very short. Yet we get in close to the black line of stability, and we're going to be very stable. Okay, still radioactive, but very, very close to stable. Okay, and now this one. Notice the different types of decay. So we've got, with this, we've got alpha particles, beta particles, emission, beta particle capture, so on and so forth. So the trend that we see here is the type of radioactive decay. All right. So if we take atomic number 50, right here, once again, we've got all of these stable marks, are all these stable isotopes. Yet, if we add too many neutrons, it has a tendency to want to go through beta decay, which, if we remember, a beta particle will jump off of a neutron and therefore turn that neutron into a proton. So it's a natural opportunity for this to become stable by getting closer to the black line. Okay, everything wants to get closer to the black line. That's the whole goal of these atoms. If we notice, if we have too few of neutrons in comparison to protons, it will want to go through beta capture or alpha decay in order to, once again, get closer to the black line. Okay? What element is this right here? If you notice, Z equals 50. So I want you to look at your periodic table. Take note of that. And you hear my guard dog in the background. Her name is Haley. She's just a little dog, but she definitely alerts anybody that may want to rob this place. Okay, there, once again, we just have this a little bit easier. Haley, come. Okay, and so now, can you define an isotope? Can you identify patterns in stability or instability of isotopes? Or can you predict likely modes of radioactive decay? And can you identify the relationship between half-life and nuclear stability? I hope you have a wonderful day. Please take the exit ticket for today's assignment. We'll talk to you later. Bye.